Hi, welcome back to the lectures on GPU architectures and programming. So, if you just recall, in the last lecture we started with the optimization, that is how to fuse multiple kernels together, and we covered the idea of inner thread fusion, one possible way to do the fusion of two kernels, and we figured out what is the relative advantage and disadvantage of doing inner thread fusion, when is it applicable and all that. With that background, we will just move to the next possible way of doing fusion, which is inner block fusion. So, the idea of inner thread fusion was very simple. We were just increasing the per thread activity, right, by making the thread do work for two or maybe some multiple multiple data points, right. So, if you just look into the example that we had, so this was our sample program for inner thread fusion. We applied it on independent kernels with in two cases. One was same number of blocks and same number of threads per block, and then we said that okay, let's allow to have different number of blocks for the two kernels while we keep the number of threads per block same, and then we generalize the concept. So, essentially we define these two operations, that for the fused kernel the number of threads would be the max of the original number of threads per block in the original kernel, and the number of blocks should again be the max of the total number of blocks in the two kernels, right. So, and we made each of the threads when they are launched for the fused kernel to perform the activities of both the original kernels, right. So, this was the sample code. So, ideally these two lines were the activities of kernel 1 and this line was the activity of kernel 2. Now, in the fused kernel they both together are part of a single thread activity based on whether they satisfy the requirements of whether they are actually valid operations for both of the kernels or not, right. Now, coming here we take a different stance. What we do is okay, we do not fuse the kernels at that granularity of threads, but we start looking into the fusion at the granularity of a block. So, what we do, if you are given two threads, you increase the block size of a fused kernel and you say that okay, my number of threads in the block should be such that some of them will be doing the activity for the kernel 1 and some of the threads in the block will be doing the activity for kernel 2. So, considering that these shaded areas represent activities for the individual kernels, when I am fusing them, this is my space containing the different launch threads, and this granularity is showing the blocks now in the new fused kernel, where essentially this represents the original block size for K1 or kernel 1, and this is for K2 kernel 2, and they together form the new block for the fused kernel. So, we will just compute a global thread ID here or sorry, a local thread ID here, that is I do not need to know what is the global thread ID, that is the ordering of the thread in a linearized manner, but we are just interested in the offset or the local thread ID with respect to this block, right. So, I just look at what is the local thread ID. So, just to recall how do I compute the local thread ID is, so you will have the parameters dot x dot y dot z, and you will like to use them with suitable multiplication factors in the x dimension, y dimension or the z dimension, and compute local thread ID here, right. So, my point is the local thread ID does not represent the exact location of the thread in a linearized manner in the entire grid, but it just represents the linearization of the threads with respect to their ordering inside one block, right. So, with that, once we compute the local thread ID and then we figure out that okay, what is the position of this thread inside this block. Is it so we decide that okay, whether to put the local threads with the smaller IDs, the threads with the smaller local thread IDs to perform the activity for kernel 1 or kernel 2, and then we write the code, and we'll put in the activities like this, that suppose for kernel 1 the number of threads per block is x, right. So, for the fused kernel we will just figure out whether the local thread ID is strictly less than this x or not, and accordingly we will make the thread do the job for kernel 1. If the local thread ID is equal to x or greater than x, then we make it do the job for kernel 2, fine. So, this is how things will work. We will have the work here for kernel 1 and then we will have the work here for kernel 2. Just to note here and the difference, earlier the same thread was doing the job of both kernels. So, we were doing a thread level fusion, inner thread fusion, but here we are doing a block level fusion. So, we are adding more threads into the fused blocks, computing the local thread ID of the thread in the block, that is the relative position of the thread inside the block. Using this relative position or local thread ID, we are computing whether this thread is supposed to do the activity of kernel 1 or kernel 2, and accordingly we are making it execute the code for kernel 1 or the code for kernel 2, right. So, if we just summarize it, so essentially we will distribute the computation of two different kernels among the threads in a single block. For independent kernels with small block size or threads per block, this is a good idea. Why? Because in case the sum of the threads per block for the kernels add up and cross the upper bound, then I cannot really do an inner block fusion, right. So, this is a good idea for independent kernels with small block size, right. So, like earlier, let STHI represent the number of threads in a thread block and SBKI represent the number of blocks in the kernel, right, where I is either 1 or 2 representing kernel 1 or kernel 2. Of course, I can generalize, I can have fusion of more than 2 kernels, right. So, this is just a candidate example where I am showing how I will fuse 2 kernels, right. So, for the fused kernel, we will have the total number of threads per block as the sum of these two, right, because I will delegate some of the threads to do the activity for kernel 1 and I will delegate some of the threads to do the activity for kernel 2, like that. And okay, what should be the block size? So, first of all, see, I am widening the blocks, right. I am not interested in increasing the number of blocks. So, the block size should not be any sum or things like that as is done with the number of threads, but the block size is rather the maximum of the block size, the number of blocks is rather the maximum of the number of blocks for each of the 2 kernels, right. So, since I have to cover both the kernels, so my number of blocks has to be the max of SBK1 and SBK2. So, when does this not work in general? So, of course, if I am trying to fuse 2 kernels where each of the kernels have lot of threads per block and the sum of STH1 plus STH2 is greater than 1024, the upper bound maybe for a higher level of architecture that would be 2048. So, whatever is the upper bound for the GPU, if the sum crosses this upper bound, then this is not working, right. So, apart from the issue with this upper bound, the other issue is that kernels with synchronization statement, for them also the idea of inner block fusion would not be suitable, simply for the reason that a synchronization statement will actually force synchronization for all the threads in a block, and it cannot work for a subset of threads which will be part of a block. So, let us come to the example of doing inner block fusion of independent kernels. So, we go back to our original examples of K1 and K2, fine. So, when we are fusing these two, as you can see that for K1 the operation was sin A plus cos B and we are storing the value in the buffer C. For K2 the operation is log2, right, and it gets stored in the buffer E, right, and when I am fusing them, all we will do is we will first define the number of threads and the number of threads per block and the number of blocks. So, we will follow the method we discussed earlier. So, we will increase the block sizes now, right, by making it a sum of the original block sizes, right, and the number of blocks will simply be the maximum of the original 2. So, the original 2 kernels had 6 blocks. So, our fused kernel will also have 6 blocks, and inside each block I just have the double number of threads, right. Half of the threads are doing the job for kernel 1 and half of the threads are doing the job for kernel 2, as simple as that. And which threads are doing the job for which kernel is being demarcated here using the different colors. So, the blue marked threads are doing the kernel job for kernel 1, the yellow marked threads are doing the job for kernel 2, which also is marked in yellow, like that. So, looking into the program example, so these are the unfused kernels, right, K1, it is not and this is the K2, right. So, when I am going to fuse these kernels using inner block fusion. So, this is the pseudocode of my fused kernel. So, first thing I will do is I will compute the block ID and then I will compute the local thread ID. I will check whether this local thread ID, again let us remember this is the local thread ID. So, the offset inside the block, this is not the global thread ID. So, we will check whether this local thread ID is less than the value STH1, that would mean that this thread is supposed to do the job for kernel 1. Otherwise, we will check whether it is inside the boundary of the total number of threads per block for the fused kernel, because if this is not satisfied, then either the value is out of bound or the value is for the second kernel's work activity, and accordingly the else if statement would fire. Now, let us just take another example. So, here we have a bit of unbalance in terms of the number of blocks. So, kernel 1 has got 4 blocks, kernel 2 has got 6 blocks. Kernel 1 has 2 threads per block and kernel 2 has got 3 threads per block. That would mean in the fused kernel we are going to have 5 threads per block and the number of blocks would be the max, which is 6 here, right. So, again we are showing that the which thread is going to do the job of which kernel. We are again showing that using the highlighting scheme we discussed earlier. Observe that in the last block what is happening. So, essentially in this picture remember one thing, although I am not showing the arrows in the other blocks, I hope you understand that the threads are present here, right. So, essentially this pattern is actually replicating here, 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 like that, right. So, just to avoid any confusion, let me just say that just like this entire pattern is also present here, is present here, is present here. But observe that I am not going to have activity for kernel 1 here, right. So, in this portion there would be no activity for kernel 1. So, what I would just have is only the K2 threads. Here I have threads for everybody and similarly here, right. But here I do not have any activity. So, I hope you understand that as the data arrangement of the kernels become a bit different, while fusing them we are introducing a absence of balance, right, because when these blocks are going to execute there will be unused slots when warps will be formed, right. So, essentially we will be losing on the occupancy of the GPU and we will be not extracting that much parallelism. So, whenever we are working with blocks or threads which are widely varying in terms of their arrangement of data, the fusion operation may not be a good choice. So, how do I handle the fusion of independent kernels if the data space size is different like this? Again we have a different number of threads per block here and also we have different number of blocks here, right. So, for that let us understand that the code is going to be a bit different. Now, these are the unfused kernels, right. So, when we are going to fuse these kernels, the first part is again same. So, I have the block ID and I am going to have the local thread ID computed using the thread IDX and block IDX parameters, that is of course fine. The next thing is first the thread has to figure out that what is its block ID. Now, why is this important? Because if the block ID is beyond the max, then of course there is nothing to be done. So just to remember, SBK here is the number of blocks for the fused kernel. STH1 and STH2 are the threads per block setting of kernel 1 and kernel 2. SBK1 and SBK2 are the number of blocks for kernel 1 and kernel 2, right. So first we will figure out whether I am really having to do some valid computation. So whether the block ID is less than SBK. If so, then you get inside and figure out whether you have some job, this thread is going to do some job for the kernel 1 or kernel 2. So the check would be that the local ID, whether that local ID of the thread is less than STH1 and whether the block ID of the thread is less than SBK1. Now just to understand why do I need this, because earlier if you see when we are doing so I am just hopping back to the code on inner block fusion for kernels with identical data arrangement. So we just were computing the local thread ID and we are checking whether the thread ID is going to do the work for K1 or K2, right. But now it's different because we have a varying amount of number of blocks, right. So I should not only check for a given thread that whether its part of its local thread ID is inside the data space for kernel 1 or it's inside the data space, it's beyond the data space for kernel 1 but inside the data space for kernel 2. The only doing that check is not going to be valid. I additionally need to check whether the block of the thread is a valid block ID for K1 or a valid block ID for K2. For example, if the block ID is this one, right, 0, 1, 2, so then in the x dimension of course, then I can understand that even if the thread ID is inside the thread boundary for kernel 1 does not have any computation for this block ID, right. So we will have a check with STH1 as well as SBK1 and then only do the computation for kernel 1. Otherwise we know that okay, there is no work for the kernel 1 and we will just check whether this is inside the boundary for the total number of threads per block. If so, there should be some activity for kernel 2, right. Now coming to some of the important points, like as we have discussed earlier, that the total number of threads per block for fused kernel should not exceed the upper bound. We have to remember this because the threads per block upper bound is architecture dependent. And so if you are trying to write a parameterized code, like whether you should really have I mean suppose you are trying to write a code where you are trying to generate a fusion of the kernels based on the GPU, right. So you may first query the CUDA device property, figure out the allowed threads per block and then you can do the sum of the setting of threads per block for K1 and K2 and then decide in the runtime whether to execute a fused version of the kernel or not, right. So that is something which can be done, like I mean you can have you can actually decide on what kind of threadings to use, whether to fuse or not. And also this was the other important point we are discussing, like CUDA does not support synchronization for partial threads in a block. So if we have sync thread statements in the reduction kernels, one of the components, then this kind of fusion is not a good idea. So moving aside into the other situation, which is inter-block fusion. So we will need to first understand what is this idea of inter-block fusion. So the first thing we did was I am just recalling back, we increased part thread activity, so that was inner thread fusion. Then we increased the number of threads per block and decided whether the thread will do the job of kernel 1 or do the job of kernel 2, that was inner block fusion. So I am fusing blocks. Now we are saying that okay, let us not do that, let us not fuse threads or let us not fuse blocks, but let us just fuse the entire arrangement of blocks together and launch a kernel. So that just means that you do not disturb the internal structure of the data space of kernel 1 or kernel 2. So you just define a kernel with the number of blocks being the sum of the original number of blocks of K1 and the number of blocks for K2, and then you let some of the blocks do the job for kernel 1 and some of the blocks do the job for kernel 2, right. So that's a much more coarse grained fusioning, right? All you are doing is you are just fusing at a coarser grain. So essentially we are executing kernel 1 and kernel 2, but concurrently. Instead of not dispatching kernel 1 followed by kernel 2, you are dispatching both of them together as a fused kernel, but nothing changes in terms of their internal coding structure. You just delegate some of the blocks to do the job for kernel 1, and then you delegate the rest of the blocks to do the job for kernel 2. So this is how it goes on. So you have the code for kernel 1, you have the code for kernel 2, you just take the block ID, you check whether it's less than whether it's a valid block ID for kernel 1, it's inside the block number of blocks boundary for kernel 1, otherwise you execute kernel 2, right? So for kernel 1 you have a progress of threads like this, for kernel 2 you have another alternate progress of threads like this, and you have a boundary here, and this is the entire grid of threads. So this denotes maybe a theoretical way to think that maybe this is x. So if you are on this side, you are executing kernel 1, for example this side you are executing kernel 2. Of course this is a 2D picture. So overall, so this would be the summary of interblock fusion. You distribute the computation of two different kernels among different blocks. For independent kernels with similar computation time, this is a good idea. Now this is important, right? Why do we say that? First of all, we understand the kernels have to be independent. Otherwise, as we have discussed, even in the case of inner thread fusion, if we are trying to fuse dependent kernels, you have to bring in sync thread statements so that you exactly know when the threads for one kernel finish, the other kernel finish, and then you do some computation. So that's quite a tricky thing to do, and it may not actually increase your parallelism that you can extract from the architecture. So overall, we are always keeping ourselves restricted to the domain of independent kernels and not going to think of using dependent kernels. Then also we figured out that okay, the kernels we should be fusing, there should be suitable amount of load balancing. The data size, the data arrangement should not be too much different. Again, the similar thing will also hold here, that we will be fusing independent kernels, but the kernels, it should not happen that they have dissimilarity in terms of computation time. Let's look at the situation. Why is it so? So then, while some of the threads we are executing this, let us say kernel 1 is a heavy kernel and kernel 2 is a lightweight kernel. So when you launch the threads executing kernel 2 finishes much faster, but these threads are still waiting, right? So that doesn't make sense then, because fusion of these threads are not making sense, because you have got these threads which are finished, but almost at the end of, they are waiting at the end of the execution, while the other threads have not ended their execution. So the entire kernel is still live in the GPU, while some of the threads are still waiting. So then you are really not exploring the parallelism in a nice way, because otherwise you could have done a fusion of these workloads with some other workloads, and that would have really led to a bit more balanced execution, right? Because overall, what is your target? Your target is to increase the occupancy of the GPU and keep on using all the architectural elements, the compute units, the memory elements, the memory bandwidth in parallel as much with as much high throughput as possible, right? So if the independent kernels have similar computation time, then this is a good idea, otherwise not. So for our case, let's understand what should be our options for fusion. So let STHI represent the number of threads in a thread block, and SBKI represent the number of blocks in a kernel. So when I am fusing them, so STH would be the maximum of STH1 and STH2. So when I am fusing kernels, STH would be the maximum of STH1 and STH2, because I am not going to increase per thread activity, right? All I am doing is I am increasing the number of blocks. So the number of threads per block remains same. So it should just be the max of the originals, and the number of blocks will be the sum of the number of blocks in each of the constituent kernels, right? So again, just to remember that this is not a good idea if workload for different thread blocks differ a lot. That means the kernels differ a lot in terms of their computation headache. So there are nice interesting points to take. For example, consider that kernel 1 is a compute intensive kernel, kernel 2 is a memory intensive kernel. Is it a good idea to fuse them? These are foods for thought. You can actually look into, you can try simulating the example of two such kernels, consider a reduction kernel, consider some other kernel together, maybe a convolution kernel, and think whether fusing them makes sense or not. Okay. Now, if we come to the inter-block fusion example, we are again restricting ourselves to the original kernels. So, we have the unfused versions on the left and the fused version on the right. So, as you can see, again we are considering the general case where we have unbalance in terms of the number of threads per block. So, and also unbalance in the terms of number of blocks, but now things are quite easy. All we do is we increase the number of blocks and we delegate some of the blocks exclusively for activities of kernel 1 and we delegate some of the blocks exclusively for the activities of kernel 2. So, that would mean we will now have, since in the original kernel there were 2 threads per block K1 and there were 3 threads per block for K2. In this fused kernel, we are having 3 threads per block in general. So, when we are fusing them, first of all you see that this is the essentially nothing but K1's working area. So, all the threads belonging to this area are going to do the job for K1. The threads which are belonging to this area, that means correct me, the blocks which are belonging to this area, their resident threads will be doing exactly the computation for K2, right. So, just to recall that all we are doing is we are figuring out the block ID. If the block IDs belong to K1's block IDs, then they are going to do the activities for K1, right. For example, if this is the block ID 0 0, this is 0 1 like that, or this is 1 0, this is 1 1, those are the block IDs for which I will have K1 working. For the other block IDs, I will have K2 working, right. So, whatever was 0 0 here, if the block ID is greater than K1's block ID, just immediately greater than K1's block ID, for that it should be this block of K2, right, and so on and so forth. We will have K2's, these are essentially nothing but K2's blocks, and these are essentially nothing but K1's block, right. But we discussed the point of load imbalance in terms of the computational natures of the kernels, whether K1 is a heavy kernel or K1 is a light kernel and K2 is a heavy kernel. But also observe the other point we mentioned here. So, first was whether the kernels have similar computation time, that was the load imbalance issue. Also observe that here when we are looking into this kernel K1, the number of threads per block is now max, right, max of K1 and K2. So, we have 3 threads for K1 as well as 3 threads per block for K2. But since K1 is originally utilizing 2 threads, so this third thread, when it is belonging to the block IDs for K1, does not have much to do, right. So, these are just threads which are getting launched without any activity. So, this is also a wastage of a thread which is running in parallel, but it has got no activity, right. So, if we look into the program example here, so fusion of independent kernels we are considering here, the fusion style is interblock fusion, but we are considering for different data space size, right. So, these are my original unfused kernels. So, of course, first we figure out what is the STH and SBK. So, STH is max and SBK is sum. Also, so we also have similar comments for the previous kernels, they are kind of repetitive. So, I am just talking about them here where it is a bit more complicated. So, assume that STH2 is greater than STH1 and SBK2 is greater than SBK1. Of course, you have to write suitable programs for that. Now, when I have this fused kernel, first thing I will do is I will figure out what is the block ID, I will figure out what is the thread ID, and I will also figure out the global thread ID. Okay. And then we will use the block ID first to figure out whether this block, this thread belongs to a block which is for kernel 1 or kernel 2. So, coming back here again they will just repeat. So, for the fused kernel we have figured out what is STH and SBK, and we are just considering where the code is written in such a way that we are assuming that STH2 is greater than STH1. So, of course, you can understand if you for your second kernel we are assuming that the number of threads per block is larger. If it is not so, just you have to switch the variant of the code, right. I hope that is clear. Here the code is written assuming K2 between K1 and K2 I have this property, otherwise your code has to be changed. I hope you should be able to do that, right. So, so first you check whether B the block ID is less than SBK1. If so, then you get inside and check that whether inside this block you have some activity for the kernel 1 or not, because if so, so you just check whether the local thread ID is less than STH1, then you execute this code. Do I have an example where this will not execute? Yes. For example, if we come here, the block ID, consider a thread this one, right. For this thread the block ID is less than SBK1, right. So, it will execute kernel 1's code, but now the thread ID is not less than STH1, right. So, it will fail the if case and it will not do any activity, right. So, for the threads with the previous IDs, they will get inside this part and do the kernel 1's activities. Those which will fail this, they are the idle threads, they do not have anything to do. Otherwise, we will just check whether the block ID is beyond SBK1 but inside SBK, then I know that this thread belongs to kernel 2. Again, we will just have the check whether it is less than STH2, the thread ID. In that case, we will delegate the activity for this thread to kernel 2's activity, right. Now, this interblock fusion also has limitations. So, what are the limitations? So, workload of different thread blocks, consider that I mean they may differ a lot, right. Consider, we are just considering the situation that suppose the workload of different thread blocks differ a lot, then this may not be a good idea. So, that was what we are speaking about, like if the kernels have different computation time and also internally if the threads per block differ a lot, right. If the threads per block differ a lot, then we will have lot of idle threads like this, and if the blocks, the activity of the block, the amount of work they have to do differ a lot, then some of the blocks, some of the thread blocks will finish, but some of the thread blocks will wait, and that will again create a load imbalance. So, if we just check here for K1 and K2, so for K1 I have, this is a heavy kernel, right, because all it is doing is doing a square root of sin A plus cos B in a per thread manner. So, is going to actually use the special function units in the SM. I hope you remember the special function units which are actually going to do the transcendental functions, right, the operations there. So, they will actually compute the sine, the trigonometric series, the mathematical expressions, the sine trigonometric series approximated for cos, and finally with the sum it will implement the SQRT operation. So, these are highly costly mathematical operations which are going on, whereas here I have a simple single cycle addition, right. So, these kernels are highly unbalanced with respect to their load, right, due to this absence of workload balancing, they are not good candidates for fusion, because fusing them I do not gain in terms of concurrent execution of the kernels, right. The kernels, because one kernel finishes much faster, the blocks for that kernel, the other kernel's blocks are still executing. So, there is not much of concurrency. So, with this we will end this lecture, and in the next lecture we will start with another optimization technique which is thread coarsening. Thank you for your attention.